Conductors in electrostatic equilibrium. What is electrostatics? It's effectively the study of electric charges that are stationary. Whereas if you look at an electric circuits, those charges are moving. For conductors, we typically think of weakly bound electrons as not being bounded to any particular metal. But metal ion, that is, but they do have thermal motions. So when we talk about electrostatics here, we have no net motion. So if I say, what is electrostatics? It's really the study of stationary electric charges. Now, they could be moving very slowly, but in general, we're assuming that they're just stationary. So for conductors, the free electrons, that is the weakly bound electrons, are free to move from one metal ion to another. So that is motion. This is a type of motion, but the overall motion, in other words, its net motion, is zero. So in conductors, so then we have in conductors, we have electrostatic. So now we want to go into the electrical. We're going to we want to look at the details of electrical properties of conductors in electrostatics. And I think I'm going to do somewhere between 3 and 4 properties. Okay, so here we go. Property number 1. So what do I know? A perfect conductor has exactly 0 field inside of it. So when you think about electrical wires, are they perfect conductors? The answer is no. So therefore, they have a small electric field inside the wires, but perfect conductors do not. To see this, we apply an external E field that interacts with a neutral, hollow conductor. Now, the word neutral hollow conductor, by definition, is what is called a Faraday cage. But I'm not here to talk about Faraday cages. I'm here to talk about properties of conductors. So let's do this in steps here. So what I'm going to imagine is that I have this. I have an infinite plane right here. And because it has an infinite plane, because it's an infinite plane, that means I have a uniform electric field. So I'm seeing a uniform electric field everywhere. And I'm going to say that this is the external, which I will then write as EXT. Now, what I'm going to place here is I'm going to place a hollow conductor. So this thing starts off neutral. And I'm going to imagine that I have something like this. Now what's going to happen is that because I have a conductor, we know that induction has to start taking place. So it's really important that you remember we start with this as a hollow, a neutral conductor. So now that I have this, let's go through some steps. So the first thing that we would see here is that we have that the external field, E external, induces a negative and positive charges. So that means here I'm going to start to build up negative charges here, because why do I build up negative charges? So when we say it induces a negative charge, what I'm really saying is that what's really happening here is that the negative charges are attracted to the positive infinite plane. So they move and they start to build up. Now, here's what happens. What happens is that the induced charges charges, excuse me, the induced charges continue to build up. So as they continue to build up, I'm seeing more negative charges coming in, leaving this positive charge to be a higher charge density at the surface. Continue to build up and create charge separation. But if I have charge separation, that means now there is an induced electric field inside the conductor. So in other words, I am seeing a field going in this direction, which is the induced field right there. But at the same time, I still have this external field because it goes right through the conductor, right? It's not a material thing. It's a field that's just gonna go right through. And then what you're gonna find here is that inside, as the charge continues to build, inside the hollow conductor, there is a superposition of two fields. And so these two fields now are going to be the induced field and the external field. So now here's what happens. And I'd say that this is the key point. The induced field starts at 0 and increases until it matches the external field's strength. So once again, the charges continue to move until you reach a state of electrostatic equilibrium. So when the free electrons stop moving, electrostatic equilibrium is now established. And what that means here is we then say that the net field inside is in a superposition of the external field minus the induced field, which then equals 0 exactly. Not almost 0, it is exactly 0. And so what happens here is that then I'm just going to take this picture right here and I'm going to pop it down here. So picture-wise, we get this type of thing. Inside of here, we find that the electric field inside is equal to 0 exactly. So a hollow conductor is called a Faraday cage. And I will come back to a Faraday cage a little bit at the end of in the next lecture here. You know, frankly, this result is quite surprising. And here's why. Because I would say that this is surprising because E inside equal to 0 implies no electrical force will be felt inside a hollow conductor. Since the electric force is then going to be the charge times the E field, we could see that that guy is 0. That is shocking. And when we get to Faraday cages, we will spend the time talking about the details of this. But we're not here for Faraday cages just yet. We're here to look at the properties. So now, here's property number 2. If a conductor carries charge, it must reside on its surface. So think about that. We have all these electrons, and none of these free electrons can be inside a conductor. I mean, that's kind of odd if you want to think about it. And, one answer you could say is that the reason why is any extra charge repels and is at the surface, implying that the net charge inside is 0. I mean, that's the way that they have to be on the surface. Now, you may not think that this is a good enough argument, but let's think about a better argument. Here's a more detailed argument. So, a better argument that charges must be on the surface involves energy. And this is something that I said earlier here, and this is just a reminder that nature always seeks the lowest possible energy state. And so when I say lowest, I'm talking about the lowest potential energy state. So let's look at several situations. Now, the first one here is that I'm going to call number 1. And what I'm going to do is I'm going to have a sphere. And this sphere right here is going to be a neutral sphere. So what do I mean by a neutral sphere? What I mean by a neutral sphere is that I have equal amounts of neutrons and protons. So this represents the lowest possible energy state. Now let's go to number 2. So now what I'm going to do here is that I'm going to come in here and I'm going to scatter some charges. So I'm going to take some charges and I'm just going to scatter them inside. So what are these charges going to do? So the first thing I should say again is that I sort of scatter, I place charges on the inside. So then what I'm going to do here is that I'm going to wait for electrostatics. So I'm going to wait to establish electrostatic equilibrium. And so when I allow this to happen, by the way, this happens very, very, very fast. Then what I'm going to see here is that I'm going to get this. I'm going to find that in electrostatic equilibrium, all of the charges have now repelled to the surface. So as we said before, we're seeing here is that the charges repel each other and move as far as possible from each other. And that happens to be the surface. Now, number 1 here is the lowest energy state, but this is a low energy state, not the lowest. It's a low energy state, but higher than state number 1. So now I want to do the exact same thing here. And what I'm going to do in this situation, I'm going to have a third situation. And in this third situation, I still place all these charges right here, right? I still place all these charges right here. But now what I'm going to do is that I'm going to imagine that I have a situation where I'm going to say is that these charges can't stay there. So the question is that these charges can't stay there unless little demons do work. So if I now look at this situation, I still have so I'm keeping all of my charges here, right? I'm trying to keep them. And the only way to keep them, because remember, they're repelling each other. So now I have all these little demons that are now pushing on these charges here. And if you look really careful, you might see these little guys at work, little horns here, right? So they're pushing down to make sure that they do not let those charges, get away. And again, these are my demons here. So if I look at this thing, because they're doing the extra work, this is a higher energy state. And the reason why it's a higher energy state is that the little demons do work to keep the charges inside the sphere. Therefore, that increases the overall energy of the system. So why are charges on the surface? Because it's a lower energy state. Why are they not spread out throughout the thing? It's because it's a higher energy state. So in summary, charges on the surface is the lowest possible energy state. Not in the inside. That's why charges must do that. Okay, so now what I want to look at here is that I want to look at another property, which I think is a fascinating property. And this is property number 3. And here's what I'm going to say here. So I'm going to say that the electric field must be perpendicular to the surface just outside of a conductor. So let's look at what we're seeing here. So if I plot this thing, okay, so if I plot this field, here's what we're seeing. So I have a solid conductor. Okay, I have a solid conductor. Now I'm going to look at its electric field. And if I look at its electric field, I know that this is at the surface here, and the maximum field is right here. So I look at this guy, and I'm seeing that right in here, we're going to say that this is the outside. We already know that on the inside, that field is 0. So if I look at the field on the inside, that's 0. The field on the outside, of course, that goes as 4 pi epsilon r squared divided by q. So I know what the electric field looks like right here. Now, to give a sense of why it has to be perpendicular, here's what has to happen. As one gets very close to the surface, the conducting sphere appears as an infinite field. Or maybe I should say an infinite plane. So if I look at this, I'm going to say that that in the limit, as r approaches big R and you get really close, the electric field of this guy, I'm saying, has to be the field of an infinite plane. So right away, if I ask the question, why must the field be perpendicular? Well, in the limit, as we get really close, it looks like an infinite plane. So therefore, that field must be perpendicular because that's the way field of a point chart of a plane field is. So mathematically, we can then write, so at the surface, we have that the electric field, which is E of little r equals to big R, well, we know that this guy must be 4 pi epsilon r squared over q, which is the max field. But if I rearrange this term, look what I see. I get q divided by 4 pi r squared divided by epsilon naught. But this is really the surface area where eta is charge per area, and in this case, it's charge over 4 pi r squared, big R squared. And that's a really powerful statement here, because you're seeing that it looks like a infinite field, but it's actually stronger. So there's two key things that we want to say here. Okay, so there are two key points. So the first point here is that an infinite plane always has its field perpendicular to the plane. Well, so do conductors. And then the second thing that I want to say here is that the field strength at the surface is twice the strength of an infinite plane. So, so then the question is that why is this the case here? Why is it that why is it the case that the E field of a conducting sphere at the surface is equal to twice that of the field of an infinite plane? Why is that the case here? So let's look at this two ways. So I would say that the physics way um, is shown with pictures. So now if I look at this thing here, what do I actually see? I'm going to say that I have a plane. And this is an infinite plane. And so when I look at this, I look at the field, and I can see here is that the field everywhere where I walk is absolutely perpendicular to the surface. But it also goes in two directions here. And of course, I have a charge field in here. Like that. So again, if I look at this field, you're seeing that this infinite plane is eta divided by 2 epsilon. So here's the thing that's really interesting to me. So now I have my sphere. Let me see if I still have it. Yep, I still have it. Well, it's not going to help me because I have charges inside. So let's just draw it. So if I look at this guy, I have this guy. So all of the charges are on this side. They're going to produce a field that looks like this here. And it's because of all of the charges on the surface is creating that field like this. But we know that E here has to be equal to 0. So when I look at this surface field, I get eta over epsilon naught. So here's the key thing to remember here. So I got to look at the charge density. So I'm going to say that the charge density here and the charge density here are the same. So if they have the same amount of charge density, then this guy has to do what? It produces two fields instead of one field. And over here, what you're seeing here is that here it only produces one field that is twice the strength. So what I mean by that is that you could imagine that if they both have the same amount of charge density, is that if that's the case, it's like I'm taking the same field, but now because I can't have an E field inside, I take this E field that was here initially, and then I start doubling it. Each of these gets doubled. And so I'm seeing a much stronger field. How much stronger? 2 times the strength. How do we show this mathematically? So mathematically, we can show this using Gauss's law. So let's start with the infinite plane. So the infinite plane here is that I'm going to pick a Gaussian cube. So then I'm going to take my field. Let me see if I can take this with me. So I'm just going to modify this a little bit right now. So then I have my field here. So if I come in here and I look at this field, what I want to do is that I need to put that cubic Gaussian. So let's say that I have a Gaussian that's going to look something like this here. I'm going to do this, and then I'm going to go back like this. Then I'm going to do the exact same thing here. And it looks like I'm going to have to extend my surface here. But ultimately, this is what we're trying to do. So when I'm looking at the E field of this for this, I have two faces that I'm seeing. So I'm going to see that if I have my area vector like this and then like that, but now I have my field. And what is my field doing? My field is coming out like this, and it's also coming out like this. But I do have a side area, right? If I'm looking at the side area right here, you can see here is that I have this little area vector here, but the electric field here is perpendicular. But there's no flux through a perpendicular side like that. So then the flux is, so this will be the flux of the cube, which is then equal to the flux of the sides plus the flux of the top face plus the flux of the bottom phase. And in each of these situations, I'm going to see here is that this is automatically zero because my electric field goes like this guy goes like that, and this right here is a right triangle. So that immediately goes to 0 by the dot product. So this is essentially the cosine of 90 degrees, which is 0. Now these two fluxes have to be the same. So if I look at this, so what I'm going to have here is I'm going to get 0 plus E times A plus E times A. So in other words, I'm going to get a flux of 2EA, and this will be just for the top face. So right away, you're seeing that the flux in this case, because I have two fields going up and down, you could see that this comes from, it comes from two fields from the top and bottom. But now if I go look at the enclosed charge, we could then say that the enclosed charged Q enclosed is going to be Q, because I can set my Gaussian to make sure that I enclose a charge Q. So then, using Gauss's law, I then have the following thing. I then say that the flux of the cube is equal to Q enclosed divided by epsilon naught. So if I look at the details, then I say that E of an infinite field, infinite plane, this field then reads that this is going to be Q over A divided by 2 epsilon naught, and then I get this 1/2 factor. Maybe I should write it slightly different. 2 epsilon naught, like this. And this is what the field of an infinite plane looks like. So now we're left with the conducting sphere. So what does the mathematics of the conducting sphere look like? So at the surface of the conductor, we then have that if we have a charged conductor, and so if this is the case, then I'm going to have a charge that originally was the same charge on the surface that we included in that. So now if I take my limit now, as R gets really close to R, what do I see? Well, we already said that we see an infinite plane. So I imagine that we have an infinite plane here. And we know already that the charge is going to be all on the surface. So this is going to be inside, and I'm going to say that the electric field in this case is 0. So now I'm going to take my Gaussian again, a Gaussian cube, and I'm going to go, okay, let's do this. So then if I start to look at the flux, we're now seeing that we have the same type of situation as we did before. So what's different is that, once again, I have an E field going in this direction. I have an area going in that direction. But here on this surface right here, E is equal to 0, which then tells me that the flux of this thing is 0 as well. So when I look at this thing, we could then say that Gauss's law shows that if I now look at the flux of the cube, I only have to consider the flux at the top face. And at the top face, this is just E times A, which is then equal to Q divided by epsilon naught. In other words, for a solid conductor, a conducting sphere, that guy has to be eta over epsilon naught. Once again, that field is twice the strength of the infinite field, which is surprising. One last thing is that now here, let's try this here. Now, what does a hollow conductor's field lines look like? So if I look at my conducting shell that we did before, I'm going to imagine that I have this. So now I look at the field. What do I know about the field? I know that the field, that there should be, that the electric field inside the shell has to be 0. So right away, I could come in here and just say, yep, that guy is 0. So why is this 0? It's because we induce charges and we have negative charges in equal amounts that look something like this. So we know that for a fact. That's because of superposition. But now the fields must be perpendicular. So then they got to be perpendicular. So if I start to draw my field lines, what am I seeing here? I see that the field line is coming here. That's perpendicular. Now, we can say that the reason why the field bends here is to make sure that it's perpendicular. So it keeps coming like, you know what, I did this wrong. So if the field is coming like this, what you're going to see here is that you're going to start to get some of the fringing. And the fringing is occurring because you're getting this field that's coming in here. Uh-oh, got the wrong direction. And then outside of here, they also have to be perpendicular. And so you're getting sort of like this type of, and it looks something like that.